Good morning, professors, and thank you for giving me the opportunity to take part in this defense session. My research topic is an investigation on the ranks of integer-valued polynomials on Gaussian integers and integer-valued continuous functions. The abstract and keywords are presented on the slide. The aim of this investigation is to extend some results about integer-valued polynomials on rational integers to include the Gaussian integers and continuous functions. We follow two chains of class inclusions and obtain the results shown on the slide. Formally, for an integral domain D with field of fractions k, a polynomial over k is said to be integer-valued if it maps elements of D to D itself. We verify that the set of such polynomials, dubbed int D, satisfies the ring axioms and forms a ring. Generally, int D is an integral domain, not a field non-Artinian, and has field of fractions kx. We first consider polynomials on the rational integers Z. A well-known result is that the binomial polynomials x choose n form a basis of int Z. Using this fact, we can construct a strictly increasing chain of ideals, implying that the ring is non-Noetherian. However, since the number of factors of any polynomial in int Z is finite, every ascending chain of principal ideals stabilizes, and the ascending chain condition on principal ideals is satisfied. Next, if a rational function f in Q adjoint x is non-zero and integral over int Z, then f must be a polynomial over Q. For all C in Z, Fc is integral over Z, and since Z is integrally closed, Fc belongs to Z, and so f belongs to int Z. Lastly, excuse R is irreducible but not prime, so the ring is not a GCD domain. We continue onward to the Gaussian integers Zi, which are complex numbers with integer, real, and complex parts. Zi is a subring of the set of complex numbers, so it is an integral domain, and int Zi is well defined. Seeing that a basis exists for int Z, we extend this result to int Zi. The union of 0 and the set of leading coefficients of polynomials of degree n in int Zi forms an additive subgroup of the Gaussian rationals. By performing interpolation and writing the polynomial of degree, by writing the polynomial in the form shown on the slide, we see that there exists a non-zero Gaussian integer a, such that ARn is a subset of the Gaussian integers. So, for example, n factorial is one such number. Next, if ARn is a subset of Zi, then it is an ideal. Since Zi is a PID, ARn is generated by a single element, say b, and it follows that Rn equals an times Zi, where an equals b over a is the reciprocal of a Gaussian integer. By definition, for each an, there exists Fn an element of int Zi with degree n and leading coefficient an. Since they have different degrees of polynomial, the set of polynomials f0, f1, and so on are linearly independent. By induction, every integer-valued polynomial with degree m can be written as a linear combination of f0 up to fn, and in other words, the set of polynomials forms a basis. Some values of an are listed here along with the corresponding basis functions fn. We make a further guess on how to compute an generally by writing it as the product of some primes in the formula shown on the slide. There is an analog in the case of int Z, where taking pi q equals q for q prime and pi q equals 1 otherwise gives us an equals 1 over n factorial. A side note is that this proof can be extended to other principal ideal domains D with characteristic 0. If f is an integer-valued polynomial on D with degree n, then for some distinct x0 up to xn in D, we can write a matrix equation AR equals B, involving Van der Waals matrix A. The determinant small a of such a matrix is necessarily non-zero, and so A is invertible. As A inverse equals 1 over A times the adjugate of A, and all entries of the adjunct matrix are in D, A inverse has entries in 1 over A times D. The column vector B belongs to D to the n plus 1, and so it follows that R equals A inverse times B belongs to 1 over A times D to the n plus 1. And in particular, AR is an element of D. In other words, we have found an A in D such that ARn is a subset of D. And from this point onward, we can just follow the same line of argument as before to prove the existence of basis. Now we move on to the ring structure of int Zi. There are infinitely many Gaussian primes which are rational integers, and for each such prime, there is an integer-valued polynomial in inset I with leading coefficient 1 over p, in the form 1 over p times x to the p squared minus x. This can be proven by substituting any Gaussian integer a plus bi into the indeterminate, which gives us the expression shown on the side. P squared choose j is divisible by p for j between 1 and p squared minus 1 inclusive, so excluding the first term and the last term, the summation divided by p is a Gaussian integer. Next, p squared is congruent to 1 mod form, so we are left to consider a to the p squared minus a and I times b to the p squared minus b. By Fermat's little theorem, p divides both of these expressions, so f a plus bi is a Gaussian integer and f is integer valued on set I. Using polynomials of this form, it is possible to construct a strictly increasing chain of ideals in inset I. We verify that this chain is indeed strictly increasing by comparing coefficients of x in fn plus 1x and inset I linear combinations of f1 up to fn. We show that for each fn plus 1, fn plus 1 cannot belong to the ideal in generated by f1 up to fn, and so the ring is non-Noetherian. And again, using the same line of argument as in inset, the ring inset I also satisfies the ACCP and is integrally closed. Since 1 over 2 times I plus 1 times x minus 1 is irreducible, but not prime, inset I is not a GCD domain. Now, we expand the scope of our investigation from polynomials on rational integers to continuous functions instead. Unlike in set I, the set of integer-valued continuous functions, CZ, does not share similar properties with inset, but is nonetheless still quite interesting. We verify that the ring axioms are satisfied, and hence CZ is indeed a ring. We find some of the properties of the units, associates, and factors of CZ. Proposition 12 and lemma 10 give necessary but not sufficient conditions, and lemma 11 here gives a sufficient but not necessary condition. We also see that a function f is irreducible if and only if it has empty kernel and maps one integer point to a prime and the rest to units. We show that the ACCP is not satisfied by choosing a set of functions that have empty kernel and take values 1 and 2 at integer points such that each function divides the previous. A corollary is that the ring is not Noetherian and not a unique factorization domain. Now that we have achieved our main objectives, we investigate whether we can extend any of our results further. Consider integer-valued polynomials on set A, which is the ring of algebraic integers. As stated in the remark, if Za is a PID, then inset A has a basis. And by following the same line of argument as before, the ring satisfies the ACCP, and provided that Za is integrally closed, inset A is also an integrally closed domain. We guess that inset A is not Noetherian and is not a GCD domain. Towards the second claim, we observe that if f is not prime, if some proper factor g divides the monic polynomial set f, then it suffices to find such an element that is irreducible. Next, consider integer-valued functions of classes Cn and C infinity. The set of such functions forms rings and follow the set inclusion shown on the side. We construct a bump function belonging to these rings, which maps one integer point to 2 and the rest to 1. By writing a set of functions in terms of these bump functions, we can construct a strictly increasing chain of principal ideals. Lastly, consider the ring of continuous functions which are integer-valued on Gaussian integers. The units of this ring are functions with non-empty kernel that map Zi to plus or minus 1 or plus or minus I. And the conditions for g to divide f are the same as Cz. The irreducibles of Czi are functions with empty kernel which map one Gaussian integer to a Gaussian prime and all other Gaussian integers to the units. By applying fn in theorem sets to the real part, we obtain functions gn where each function divides the previous, so there is a non-terminating chain of principal ideals. Here are some of the books I referenced. Thank you for listening to my presentation.